So we've seen that we can study the geometry of a space by looking at loops on the space, locally constant functions, so those functions for which the derivative is equal to 0 everywhere, and irrotational vector fields. These locally constant functions and irrotational vector fields, they're really the same because curl being 0 is the same as the derivative of the vector field being 0 if you interpret this in the right way. So what we've really seen is two different ways of looking at the geometry of a space. We've looked at loops on the space and we've looked at locally constant functions. So notice that loops on the space are just functions gamma, let's say from the interval 0 to 1, into x, while locally constant functions on x are functions out of x into the real line. In particular, loops measure the geometry by looking at maps into x, while locally constant functions study the geometry of the space by looking at functions out of x. So this is an example of something called duality, and is one of the most important concepts in mathematics. Okay, so at this point you're probably asking, so what does this have to do with Euler's number being geometric? What do loops and vector fields and locally constant functions have to do with numbers, let alone Euler's number? So we've seen this duality between loops on x, which we denoted by gamma, and functions out of x, which we called f, whose derivative was equal to 0 at every point. Now, how are these related to numbers? That's the question we're trying to answer now. So one thing we can do is we can bridge them. There's an interface between this duality, which is given by the integral. We can combine loops and functions via integration. And at this interface is where we get a real number. The integral outputs a real number. So on one side of the coin, we have loops on the space. On the other, we have functions out of the space. These are like two sides of the same coin, which are bridged via the integral. And at this interface, we have numbers. In around the year 2000, Kontsevich and Zagier called such numbers periods. So a period is a number which lies at the interface between this duality. So note that the functions, or more precisely the forms, are required to be rational functions. That is, we need the functions f to be ratios of two polynomials with rational coefficients. Moreover, the loops, or the regions of integration, need to be given by polynomial inequalities with rational coefficients. The reason for this is that if we allowed real coefficients or complex coefficients, then there would be too many periods and it wouldn't give us a candidate that we wanted. For precise statements, I recommend seeing the Kontsevich and Zagier article, which is linked in the video description down below. So we can see that pi is a period. So the first thing we need to do is find a region to integrate over. And we also need to find a rational function to integrate. And pi shouldn't be too bad because we can just take the unit circle, which is given by x squared plus y squared is less than or equal to 1. And in which case we can just take the function to be 1 identically. In which case we see that pi is given by the integral over the unit circle of the function 1. So pi is certainly a period, and this tells us that periods are a better candidate for geometric numbers in comparison with the perhaps less convincing constructible numbers. So I'm now going to pose the question and ask whether you can show whether the natural logarithm of 2 is a period. So again, we need to find a region to integrate over and a rational function to integrate. The region I'd suggest integrating over is given by bounding x between 1 and 2, bounding xy by 1, and bounding y from below by 0. In this case, we can again take the function to be 1, and then ln of 2 is given exactly by this integral here. So this shows that the natural logarithm of 2 is a period, and I'm going to ask you guys to look at this integral and try to figure out why does this region work? What is this region? What is it geometrically describing? So periods appear to be the candidates for geometric numbers that we've been looking for. But is Euler's number geometric? That's the whole point of this video. Is Euler's number a period? Well, it turns out that we don't know, but it's conjectured that Euler's number is in fact not a period. So as a consequence, I'm going to leave the following homework problem, which is to use this theory to determine whether E is a period. And if you have a solution for such a problem, please let me know in the comment section down below, and feel free to post it to the archive.